Alright. Dropbox, DIFC, slides, physics, fields, number 2. Can you see okay? I should move a little bit, should I? You can all see okay? Are you sure? Okay, electric field strength formulas. Got that? Got that, yeah. Andak?
Yeah.
Yep, okay. We're really going to look at adding 2 more formulas to the one we did last time. Remember the one E equals F over Q. So we're going to add to that now. Just before we do that, we need to talk about how different charges put together in different ways will make different electric fields. And we'll look at 4 types for the exam. So what we're going to look at is what electric field do you get if you have just a point, symmetrical sphere, parallel plates, and a dipole. So the first one is if you have a point. Now, I kind of talking about this last time, so just to explain, remember we said an electric field is which way a positive charge would move. Okay, so you can understand if you put a positive charge here, it will move out. And if you put a positive charge here around a negative, it will move in. So this is the electric field around the positive charge, and this is the electric field around a negative. Now, before you draw this, maybe you just want to put a line between them because these are 2 separate examples. They're not together, okay? So this is for a point charge. Point charge. Got that? Yep, makes sense? Andak?
Yep.
Continue. The next one is if you have a sphere. So here's just one example. It's the same idea if it's negative. So imagine you have all positive charges grouped together, just like a collection of positive charges. You actually get the same type of field as if you have just one positive charge. So the point here is that the electric field like combines to make a stronger electric field. And the same idea for if it was negative as well, okay? So if you can draw this, this is for a spherically symmetric charge. Got that? Yeah, continue. Okay. Now the next one, parallel plates. This is when you have, it's a bit like with capacitors actually, you have 2 plates. One of them has a positive charge and one of them has a negative charge. So the way you can actually do that is, come on. Come on. There we go. The way you can actually do that is if you have 2 copper plates and you connect it up to a cell or a battery, a positive end here. Hey, who did I get? I got Matt. And you get the electric field going down like this. And this is the positive plate and this is the negative plate. Okay, so that is what it looks like between a positive and a negative plate. The electric field points down, and it does actually curve out a little bit at the edges here, if you can try and draw that too. Did you get blown away, Matt? Huh? You walked? Oh, you're very good, you cycled. You didn't fall off your bike. Good job. Okay. No, you need a minute. Got that? Siba, got it? And that? Yeah. Okay. Now, the next one. Come on, don't be stuck. Loading. Dipole. Now, this is just one example, the dipole. You actually have three possibilities. You could have a positive and a positive, a negative and a negative, and in this one here, a positive and a negative. So it's not really much different to just a positive and a negative by itself. Like if you had just a positive, the field would look like this, wouldn't it? And if you had just a negative, the field would look like this. So the only difference is in the middle here they actually combine, because if you put a positive charge here, it'll be pushed away by that and moved in towards that. So you can see here in the middle all that's happening is they're combining. So the field is strongest here because you're being pushed by the positive and pulled by the negative. So it's like the field lines combine together in the middle there and work together. Okay. So this is a dipole, a positive and a negative. One of the questions in the workbook you'll have to do later is you have to try and draw what you think a positive positive and a negative negative might look like then. Okay. But I think for the exam, yeah, they kind of usually ask for this one in the exam, a positive and a negative. But I mean, they could ask for positive, positive and negative, negative. But usually dipole means one positive and one negative, I think. Why don't you draw that? Let me just check. Dipole. Yeah, so dipole usually means positive and negative. But just in case, it's good to practice the other ones for the exam too. Okay, got that? Was that drawn?
Just a bit.
Oh, yeah, no problem. You have that match? Yeah. Oh, Matt, I found out you're not the top math student. You know, I think there's somebody got a 99.
Yeah.
A 99? I do wonder if getting a 99 makes you happy or sad because you're one away from 100.
No.
Huh?
No.
Done? Okay. Continue? Yeah, okay. So, where's my cursor? I can't, there it is, okay. Right. Now, new term, something called equipotential. Maybe you can work this out. You know the word potential. Potential means like potential energy. So what do you think equipotential might mean? So what does the prefix equi mean? No? Do you know any words that start with equi? No. Equilateral triangle? No? Okay, I'm teaching you something new. So, the English prefix equi means equal. Okay? Do you get that, Matt? So the prefix equi means equal. So equipotential, it looks like this. Well, actually, no, before I said. So what do you think that might mean, equipotential? Any ideas?
Potential.
Yeah, what about the potential? Nobody wants to? Sibyl? You want to try? That's correct, yes. Are you guys just tired or not feeling the energy? Equipotential is the part in space where there's the same potential energy. Now, before you draw that, or before you write that, let me draw that with an example. So, let's say for example, here's the grass, and you know that potential energy equals mgh. So if I had a ball here, it has potential energy. If I just move the ball here, it has the same potential energy, right? Because it has the same height. Agreed? Yeah? So, everywhere on this line has the same potential energy. Everywhere on this line has the same potential energy, and this line here. So like if this is 1 meter, 2 meters, 3 meters, all these lines have the same potential energy. So these are called equipotential lines. The lines where the potential energy is the same. That's the definition for it. It's the part in space where every point has the same potential energy. And I already drew some of these. Got that? Okay. So what I want to do next, in the 4 pictures I gave you, I want to draw in the equipotential lines. So the first one, what was the first one I gave you? Was a single charge, like a positive, like this. and the field lines go out like this. Now, the equipotential lines, you've done well, have you done energy levels in chemistry? You've done ionization, you've done orbits. So, have you learned that if an electron is in a higher orbit, it's easier to remove? Or you've learned that? Yeah, okay, good. So, remember we said if it's trapped, what do we know about the potential energy? Positive or negative if it's trapped? Oh, you forgot this? It's negative, yeah. So, if it's in a high orbit, it has a low potential energy. It's easy to remove, okay? And then as you move it in, you have different energy levels. So this, I hope this isn't surprising because of your chemistry, that the energy levels look like this. That in each different orbit, you have a different potential energy. And actually what's happening is the potential energy gets closer to zero as you move out. This means that the electron is, or whatever it is easier to remove. Yeah. So that's something that they ask in the exam. They sometimes ask you to draw the field lines and also the equipotential lines as well. So in the diagrams you drew, maybe in a different colour, could you add in the equipotential line? So that's the first one. Yeah? Did you add them in, Siva? Are you confused? What's confusing you?
What lines?
The black lines I drew. Because I think in your picture you only have the blue lines. Yeah. Yeah. So if you can add in the black circles then. Okay. You got that? Yeah? You won't be shocked to discover that for the next example, the sphere, it's the same deal. So if you want to just put circular lines around the second example.
The black line is the equipotential line.
Equipotential line, yeah. Got that? Yeah, continue. So the third one, was the third one the plates? Yeah. So remember the field lines look like this. You have that. And it curves out a little bit here at the end. And this one, the equipotential lines are just like this. They're just horizontal lines. Like that. Got that? Yeah? Continue. Yeah. So the next one, which way did I put the positive? On the left or the right? Positive here, negative here, yeah? And the field lines look like this. Wasn't it like this? Yeah.
The arrow pointing like minus.
Huh? What did I do wrong? I go. Can you describe what I did wrong?
Isn't the arrow pointing minus?
Pointing to the minus. Yeah?
Well, now for the minus, it's pointing inwards for the negative.
Oh, sorry.
Yeah.
I see now. I have my arrows on this one pointing the wrong way. Thank you. Of course, pointing inwards here, like this is what you meant, wasn't it?
Yeah.
Yeah. Thank you. Thank you. Okay. So here, the equipotential lines are the hardest to draw. They're kind of like circles, except here in the middle they kind of combine. So I have a picture here. Try your best. Now it's circles, but the circles kind of spread out like this. If you can get me, they're kind of getting wider at the right, and they're kind of squished in here on the left. Okay, same thing here. So you have a circle, but it's kind of squishing in and spreads out on the left like that. Okay, and then the middle, you have a vertical line here, and then you kind of have something which is curving around these circles like that. Oh goodness. That's the equipotential for the dipole. It's difficult. Got that? Yeah. Let's have a look. I can continue? Yeah. So, I've drawn those for you. Right. Last time we had a formula for electric field strength. It's F over Q. Yeah? Now, if you have two plates, they produce an electric field, and we want to know how strong this field is. Okay? And it actually, you can work it out. It depends on the two things. It depends on the voltage in the cell and the distance between the plates. So you have this actually simple formula. Tell me before I continue for the formula for E. Do you think the E is bigger or smaller if the V is bigger? What do you think? Will this make a stronger field or a weaker field if you have more voltage here? Stronger. So we think there might be like a V on the top. What about the D? What might the relationship be between the D and the electric field strength? Yeah, what do you mean? Like, imagine I made the D bigger. What would happen to the E? Yeah, be less. So you're not perhaps too shocked that the formula is simply V over D. Yeah. got that, see about? Yeah. And deck?
Yeah.
Okay, continue. So, this one is a hard one. How strong is the electric field around a point? So, whatever, we'll just say positive point. So, what do you think might affect how strong the field is? Well, if this distance is bigger, do you think the field will be stronger or weaker at this point? What do you think? Be smaller, wouldn't it? What about if you had a charge here, a bigger charge, then the field will be stronger. So the formula, it depends on how far away you are and how much charge you have. It's equal to this. I'll write it down here so you can see it as well. 1 over 4 pi epsilon 0. This is a constant. And then it's times this q here over r squared. Okay. Now, like I said, this is a constant. This e here is on your calculator, not your, it's on your one, Matt. So if you don't have it, you'll need to write it down. The value of epsilon 0 is 8.85 times 10 to the minus 12. And before we write this down, let's just see what the units are. So let's just work out the units here. Now, epsilon 0 equals 1 over 4 pi e q over r squared. What's the units for electric field strength? Do you remember the formula for it last time? Yeah, newtons per coulomb. And what's the unit for charge? Q. What is it? Coulombs, yeah. And the R is meter squared. So the unit for this is coulomb squared per newton per meter squared. It's one way you could write it. Okay. Right, so yeah, I don't know what you want to write first, but that's the units for it anyways. And as I said, this is on the calculator. You found it on your calculator? Is it on yours?
Sure.
I think this formula is in the book.
So
Yeah.
if the formula book gave the value of E0, then if I use the value of the calculator, then the answer is incorrect. So
Yeah, I know. Well, it depends what you mean by incorrect. Your answer is more accurate. But it only... You just need to be right the three significant figures. You know? Are you asking me what you should do in the exam?
like follow the value on the
It's a tough one, Matt. But maybe it's safer to follow the ones in the formula book. They're written on the front page, you know, so you have them. Continue? No? Yes? Right. Let's have a look, I think, at some examples now. So here's the first one. Two horizontal plates have 200 volts across them. The positive plate is a centimetre above the negative plate. So this is what it looks like here. You have the positive one on the top and the negative one on the bottom, and between them is 1 centimetre, and the voltage here is 200 volts. And you have a little particle here, and it is half a milligram, so 0.5 times 10 to the minus 3 grams, and that's equal to 0.5 times 10 to the minus 6 kilograms. So that's the mass of this guy, okay? It also has a charge of 10 to the 10 E. So because it has a positive charge, it'll be pushed down and pulled towards the negative plate, okay? My question is, what is the time it takes to fall? So you can think of this as UVATS, UVATS. What's the U? We know it, it's 0. What's the V? We don't know it. The A we don't know, the T we don't know, and the S is minus 0.01. Now, how could you work out the A? You could use Newton's formula. A equals F over M. Do you know the mass? You do. However, what is the force acting on this? What forces are acting on this? Yeah, there's one from the electric field, and also there's its weight. Yeah? So, what's you know the formula for weight, of course, don't you? And then also, what is the formula for the force for the electric field? We did that last time. Yeah, EQ. Now, do you have a formula for E? From today, you do. What was the formula for the E between electric plates? V over D, okay? And just to be careful, what I do is you want to make sure that answer is a minus, because in this picture I'm taking down as minus and up as positive. So we have enough information here to work out the T as soon as we work out the A, okay? I think you can do this one. I think I've set it up so that you have everything you need. I also feel like the answers you get will be really, really small. I think what will happen is the electron will just, fire down. So don't be surprised if you get a small answer. Let's see what you can get. Can you see okay, even with my head here? It's okay? Oh, yeah. How are we doing? I don't hear any calculator tapping yet.
What is 10 power 10?
What is what?
10 power 10.
10 power 10 E is the charge. That's the Q. 10E. I gave you the E earlier in a previous class. It's the charge of the proton or the electron. Okay. The T, the time. Do you want me to do it now? Or what's the story? Shall I do it now, guys? Or do you think you can get it? Okay, I think I should do it now. Do you have an answer, Matt? Is that yes or no? Okay. So look, well I hope, okay, let's look. A equals minus, the weight is mg, so the m is 0.5 times 10 to the minus 6 times 9.81. Oh dear, goodness sake. I'm sick. Continuing. Plus, and this is all over m, which is 0.5 times 10 to the minus 6. Now, here we have EQ. I know the Q. The E is the voltage, which is 200, over the distance, which is 1 centimeter. And then we multiply this by the charge, which is 10 to the 10 e. And what's the value of e? It's like 9 point, no, 1.6
1.602.
times 10 to the
1.890.
minus 19. Okay. I saw you rubbing something out. What was your mistake?
Oh, I used the mass of electrons.
For what? Oh, down here?
And
Ah.
Sir, can you use it in the certificate or?
Down?
No, I mean this, because it's not showing the full.
Oh, I'm cutting it off, am I?
Yeah.
You need me to move it this way?
No.
Maybe I just need to move. That might be the easiest thing.
No, it's because one of the screens.
Oh, I see. I understand. That's a bit better, huh?
Yeah.
Okay. So you made that mistake, and what about here? And Siva, how did you do? So you just had E. Right. Once you write this down, can you tell me what number that is?
The E is from the question. Maybe the 10 power 10.
Yeah, it's in the question. Yeah. Thank you, Matt. What is it?
73.9.
Pretty big, huh? So what's the formula that would give us the T if we know U, A, and S? S equals, I think. So S equals UT plus a half A T squared. So T is the square root of 0.02 over 73.9. Okay. Problem, Siva? Oh, I just brought the 2 up to the 0.01 and then brought the 73.9 down. I brought that up and that down. Is okay? Are you sure?
0.016.
0.016. So 16 milliseconds? 16 0.5 milliseconds. Okay, is that okay? Are you sure? I don't know if I can trust you. No, I'll trust you. Alright, continue. Andek? Right. An electron is 2 millimeters from 3 protons. So you have 3 protons. 1, 2, 3. Plus, plus, plus. And you have an electron here. And the distance is 2 millimeters. And we want to know what's the force. Okay. So the force, what's the formula for the force? For the electric field here? EQ, very good, yeah. Now, which formula do we use for the E now? To calculate how strong the field is. Which one? No, because that's when you have two plates. So, do you understand? Like the V over D is when you have two plates, like parallel. You use the other one, the one with the epsilon 0 in it. Yeah? So, that is 1 over 4 pi epsilon 0 times some charge over the distance squared, which is 0.002 squared. Now, what charge do I put on the top? Do I put the charge of the electron or the 3 protons? What do you think? Everyone thinks the electron, yeah, but it's the 3 protons because it's the 3 protons that are making the field. So here is the 3 protons, and then you multiply that by the charge of this guy here, which is E. So this can simplify down to 3E squared over 4 pi epsilon 0, 0.002 squared. Yeah, so when you're ready, you can tell me what that is.
Why the charge of why we use protons?
Yeah, so the difference is here and here. This is the force experienced by a charge Q. So that Q represents the charge of the electron because that's the one that feels the force. This E is the electric field, and this is caused by the 3 protons. So in the formula for the electric field strength, it's 3 protons because that's the cause of the electric field. I can't think of any example that's like this in something else we studied. What were you thinking?
Even the electrons pull the 3 protons.
Now, very good. You are right, but the electron is pulling the 3 protons, but we often, for simplicity, just think about the... Here, I'll put it this way. Which is pulling on which? Does the sun pull the earth or the earth pull the sun?
The sun pull the
Yeah, it's the same logic here. You say the 3 protons pull the electron. Even though, technically, the earth is also pulling on the sun. It's just because you have something big and something small, we just imagine that the only thing that's happening is the big thing is pulling the small thing. But at the same time, the small thing is pulling on the big thing as well. So it's not that you're wrong, it's just that it makes it easier for us to think about it as big thing pulling on small thing. Yeah. Yeah. What, did you get that, Stephen?
1.73
Yeah.
times 10 to the minus 4.
Newton's then. Is that okay? Yeah. Can I continue? I probably have another example, do I? No, I don't. Okay. Thank goodness for that. I felt like I was killing you or something. I'm not sure. I know the field stuff is hard. Your opinion, please. Do you think you could handle another field lesson? See, I'm looking into your eyes and I'm not so sure. Because what we could do is we could work on the questions in the workbook, and then in a few minutes what I could do is I could do the questions from the last lesson. And I could even do some questions from today's lesson if you've tried them first. I don't know. Or maybe I should wait until next week. How did you do in the last worksheet? Were there any hard ones? What was the last one? That was the only hard one? And then, I know in the lesson we have today, these are harder. They're all kind of hard. Why don't you try these questions for 10 minutes, then I can do the answers from the homework, and then maybe we'll work on some of these ones together after you try them. So it'd be wonderful if you could get question 1 done.
What's the answer?
For which one?
This one.
Oh, it was, here, I'll put it on the screen map.
I can remember this.
Well, that's what Siva told me. I trust her.
I got 22.
Oh, who do I trust? Did you type in E as 1.602?
I got minus 22 power.
You got a minus what power?
22.
That's very different to 12. That seems too small, Matt. I think I might trust Siva on this one. Can I see what you typed in? No. Let Matt do it again. I trust you. Oh no, it's gone from your calculator, is it? I know, don't worry about it. You can start that one.